Greetings, everybody. So on this video, we're going to explain the bifurcation diagram, which is generally used for any type of chaotic system. But of course, we are going to explain this using one of the most well-known systems, which is the Lorenz one. So let's begin. First of all, let's discuss some basics on continuous time systems. Okay. So remember, we are talking about continuous time. So the time interval under study is continuous. It's not discrete. And usually here we consider a time that starts from some fixed point in time. Let's say t equals 0 and the time goes to infinity. Although in some physics textbooks, you may see something more general, like time going from minus infinity to infinity. Again, here in this case, the evolution of the system is given by a set of differential equations. So the general format is x dot, where x is the state of the system, is equal to some function of x, so some function of the states. And of course, for these types of systems, we generally, use them to describe, we can say in general, flows. What does that mean? Differential equations are used to describe circuits, any type of mechanical system or robotic system found in nature or artificial, any sort of fluid motion. We can generally say any sort of masses that are interacting in the environment. So these are the types of systems that are described by differential equations. Okay. And in the general case, especially the nonlinear, of course, which we are going to discuss, you will find it extremely difficult, if not impossible, to find a closed form solution for the system. And by closed form, I mean an analytical expression, okay? You will not be able to find that usually, which means that these systems are solved numerically, okay? So we are using any type of numerical integration method. MATLAB has a lot, the well-known Rank-Yakuta, for example. And of course, this means that although the time is considered continuous, we usually perform some sort of discretization, ideally over a very small step, like, we start from 0 time, 0.01, or maybe even smaller, 0.001, and then we iterate step by step and obtain the solution of the system. Okay, so these are the general information about differential equations and continuous time. Okay, and remember, very well-known fact, to have a chaotic behavior, you need to have 3 or more dimensions. Okay, and this means 3 differential equations or more. Okay, in 2 differential equations, if we are not, explicitly dependent on time, we cannot obtain chaotic behavior. Okay, so these are the general stuff. Now let's move on to the Lorenz chaotic system. Of course, you may have heard that the Lorenz attractor, very well known, discovered by Edward Lorenz. It's, I guess, the most famous system of differential equations that generates chaos. It is a set of 3 differential equations. So we have 3 states, x1, x2, and x3. And the system also has 3 parameters, sigma, rho, and beta. Okay. You can set the parameters to some fixed values and solve the system. Okay. So this is a very well-known system for chaotic behavior, but actually it has a much richer behavior. So it doesn't necessarily behave chaotically. It behaves in many different types of behaviors. And the bifurcation diagram, as we're going to see, actually is a method to understand when it behaves differently, depending on the parameter values. So this is the system. And okay, let's solve it. So I set the initial conditions of the system, the initial values, x1, 0, x2, 0, x3, 0 to 0.1 for all the states. And I set sigma equals 10, rho equals 28, beta equals 8/3. Okay, this is the more standard form of parameter values. I mean, if you look out the Lorenz system in Wikipedia, these are the chosen values. Okay, so this is the most common set of parameters to solve the system. So after I solve the system, I obtain these 3 time series. Okay, x1, x2, and x3. And the system here is chaotic. But how can I understand that? Okay, what does it mean, basically? It means something very important. First of all, that it is bounded. This is very important. The system doesn't go to infinity, right? So it remains bounded for all time. But the trajectories never repeat themselves. Okay, so you see the time solution here, and this time solution is for 200 seconds. Okay, if I were to simulate it for much longer, say 1,000 seconds, 2,000 seconds, 3, 10, a million seconds, this trajectory would never go into a repeating pattern. Okay, so there will never be a pattern in the system trajectory. The trajectory will never repeat itself. Okay, and this indicates the fact that the system never falls into period. Okay, so this irregularity in combination with the fact that the system is bounded means that we have a chaotic behavior. Okay, as long as we have one more condition that I'm going to show. Of course, you are very well aware for the so-called Lorenz butterfly attractor. What do I do to obtain this? I pretty much I do something very simple. It's called the Fels portrait. Instead of plotting all of these three states with respect to time, I plot them with respect to each other. Okay, so I plot x1, x2, and x3 on the same graph. Okay, and of course, you can do it in the two dimensions, x1 with the x2, x2 with x3, and x1 with the x3. Okay, so this is the phase diagram. So it shows us the interrelation of the states along with time. And of course, by plotting this, I obtain this very well-known graph. It's called the butterfly attractor. It's sort of a double helix, a double wing attractor. You can see many different names in practice in different books. So this is a very well-known chaotic behavior of the Lorenz chaotic system. And actually, the system here has one very specific and important property. This is again called the butterfly effect. This effect is known also as the sensitivity to initial conditions. It's sort of a more formal definition. What does this tell us? Let's see these two solutions here to understand this butterfly effect. These solutions are for all the same parameter values, so sigma, rho, and beta are all the same for both systems, and the initial conditions are slightly different. Okay, so they are almost identical, but not exactly the same. X1 is the same, X2 is the same, and X3 has a slightly different over the 1, 2, 3, 4, fifth decimal point. Okay, so the difference is minuscule, as you can understand. So I take these two systems and I solve them, right? The first one is in black and the second is in blue. And if you see the solution here, you will observe that for the first 20 or 25, 30 seconds or so, you cannot observe any difference, right? I mean, the black trajectory which is below isn't really obvious. But what happens is this. Just over time, it takes around 30 seconds, little by little, the two trajectories start to deviate from each other. Okay. And although for the first 30 seconds or so, they are almost identical, before they even reach 40 seconds, they deviate completely. And from now on, they are completely different. So you see that after this initial time, the blue and black trajectories for all three states are never the same. Okay? And this is the butterfly effect. It tells us that for a chaotic system, trajectories that start very, very close to each other, over a very small amount of time, they will begin to deviate from each other and they will never be identical again. So this is the butterfly effect. But observe something magical. Although both trajectories are different from each other, both, if I plot them as a 3D phase portrait, result in the same shape. So although these two trajectories are different, if I plot them, they have both of them the same sort of helix double wing shape. Okay, and this is the attractor of the system. It tells us that different initial conditions, they deviate from each other, but they end up all in the same attractor. Okay, so this double circular shape here is called the attractor of the system, right? So this is the butterfly effect for chaotic systems, right? But of course, this is the most well-known and reported behavior in the Lorenz system. But in actuality, the Lorenz system doesn't have just this behavior. It actually has many more behaviors. So let's see about this. Okay. What do I do to unmask them? Let's say we have the initial conditions fixed to 0.1. Sigma is fixed to 10. Rho is fixed to 28. And I will see what happens when I change the parameter beta. Okay, previously I had it to 8/3. Now let's change it and use it, let's say beta is 0.5. I set these parameters and I solve the system. Okay, what do we see here? Initially I see some bounce, some bouncing on and off, but then the system stabilizes into this behavior. So you will see here that, previously we didn't have a repeating pattern. It was always irregular. But now this pattern is periodic. What does it mean? It means that it is very regular. It repeats itself. The trajectory of the system goes around again and again and again to the same positions. That's true for all three states. Okay, and obviously it is much clearer if I plot it as a 3D phase portrait. Okay, you will see here that the shape is similar but not the same as before. It actually has a double circular shape, a double wing shape again, but it is a fixed trajectory. Okay, it goes around like that, sort of reminds us of the infinity symbol, but it doesn't deviate from this fixed set of points. Okay, so this behavior here is not chaotic, obviously. It is periodic. The thing is, you might have heard that the periodic behavior of the system has different levels. So it period 1, period 2, period 3, period 4. You might have heard about that in a book. But what does this mean? Okay, so for example, here the system is periodic, but it has a specific amount of period. It has period 1. Okay, this level, the period 1 level, means that the system has a very specific pattern. But how we can understand that? How we can signify and quantify what period I have? Okay, to quantify the period level, there is a very well-known process which has to do with what is called a Poincare cut. It's an amazing visual representation of the period, and let's see what it is. To understand what level of period I have, I do this specific process. I take the previous trajectory, this one right here in the 3D space, and I take a plane of intersection. Now, this plane is not fixed for all systems. You have to choose it yourself. Okay, so for a different system, you need to first observe the attractor and realize what is your plane of interest. Here, for example, I observed that this system goes around from x1, if you see right here, from -10 to 10. So always x1 equals 0 is around the middle of the attractor. Okay, so I choose as a plane of intersection that I'm interested, the plane x1 equals 0. Okay, if you see the graph here, it's like taking a knife and cutting through the diagram, right? So if I take this plane, this attractor intersects it, right? And it intersects it on two different points, okay? As the trajectory goes around, so it intersects this plane one time going in and one time going out. Okay, when I say in and out, I mean, forward and backward. So this trajectory in the 3D space intersects my plane twice. But it's something interesting here. Although it intersects it twice, if I actually choose a direction, of course, I choose a direction having to do with the derivative, right? So for example, here I chose a negative derivative. This means that as x1 increases, it intersects it once, and then as the derivative decreases, so x1 becomes lower, it intersects it to another direction, okay? So one's going in and one's going out. So if I choose one of these directions, I can realize that actually we have only one intersection with the plane, okay? So this is what we do. Although we have two intersections, we kind of decide which direction we want. Does it matter? No. You just have to stick with one choice and go throughout, the whole simulation for the bifurcation diagram. So here I choose negative derivative. So this trajectory, this phase portrait, intersects the plane only once. Okay, this plane x1 equals 0. And this tells us that this system, for these parameter values, has a period 1 behavior. Okay, because we have only one intersection with the chosen plane. Okay, so using this Poincare cut, I can immediately quantify the level of periodicity that I have. So this system has period 1. Let's see what happens next. So previously I had a beta equal to 0.5. Now I set it to 0.55. Okay, I simulate the system again. Again, I discard these initial values right here, which is the transient behavior. We don't want that to quantify the behavior of the system. We want to see how the system behaves after this transient diminishes. Okay. So again, the system's behavior seems to be some sort of pattern-like, right? Not the same as before, but again, I see a very clear pattern here. So probably I'm going to have periodic behavior. But let's see what happens in the 3D space. Nice. The shape is very similar to the previous one, but you will see now that again I have this sort of double circular shape, but now I have two circles going around. Okay, so as it goes like this, it sort of follows a double pattern, right? So now, how can I understand what sort of behavior I have? Obviously, it is periodic, but what level of period do I have? To understand this, again, I do the exact same thing as before. Okay, uh, I take this plane of interest, which is x1 equals 0, so the same plane as before. I also choose a direction of interest, let's say negative derivative, so going from the positive values to the negative values of x1. And I observe here that I have two intersections with the plane, right? Actually, I have four, as I said, two going in and two going out. So with this given direction, I have 2 points of intersection with the plane, okay? So this tells me that I have a period 2 behavior. So again, similar to the previous case where I have periodic behavior, but on a different level. Previously, we had period 1, and now we have period 2, right? So a very clear distinction between the two behaviors. Again, for beta equals 1, what does it happen? You will see that the parameter, the trajectory, I'm sorry, now becomes again irregular. So probably if I plot it in 3D, okay, yeah. Now it's very clear. Again, I have chaotic behavior, right? Because I have irregular patterns. And again, the Poincare cut will give me this information, right? So again, by taking the Poincare section on this same plane, x1 equals 0, and on the same direction as before, negative derivative. Again, what do we see? I will see that I don't have one intersection, I don't have two, I don't have 10 intersections, I have numerous intersections, right? There are much too many to count, really. So this is a clear indication that the trajectory as time moves around intersects this given plane in numerous different positions. Okay? And the fact that I have so many different intersections with the plane tells us that the trajectory is irregular. So clearly here that I have too many intersections, the behavior is chaotic. Okay. So this is a great way using the Poincare section to quantify how much, if you like, or what is the level of periodic behavior that I have. And in case I have too many intersections, I can indicate, it indicates that we have a chaotic behavior, right? So as you see, the Lorenz has far too many different behaviors appearing. So let's move on to the bifurcation diagram, right? So what does it do? What it represents? Uh, that's the whole point behind the bifurcation diagram. Okay, having a system like the Lorenz one, which has too many different behaviors. It has period 1, as we saw. It has period 2. It has also period 4 that we didn't see. It also has chaotic behavior. And all of this happen for different values of the parameter beta. Okay, so what do I need? I need a graph that will somehow tell me that how the system will behave for different parameter values. And this is the bifurcation diagram. That's what it represents. Okay. It tells us what is the qualitative change in the system's behavior as we change one single parameter. Okay. So it is always computed with respect to a single parameter. Okay. And by observing the diagram, we can see for what parameter values we have periodicity, and what parameter values we have chaos, but we can also observe how we transition from periodicity to chaos. I'm going to explain this. So the diagram here, what does it have? On the x-axis, usually it has the value of the parameter that we want to study. And on the y-axis, it gets some sort of measure that will tell us what is the behavior. And specifically for this method, what we plot is the points of intersection with a given plane. So we can immediately understand if we have one intersection, two intersections, 3, 4, 5, or many intersections which indicate chaos. And from this, we can understand qualitatively how the system changes. So let's see how we can compute it. Okay, it's very simple. Actually, it is a single for loop. So let's say we have the Lorenz system under study, and I want to study how the behavior changes when I change the parameter beta. Okay, so I have chosen my parameter beta. So now we need to set fixed values for everything else. So I initialize sigma, rho, which are the other parameters, and I also initialize my initial conditions, x1, 0, x2, 0, x3, 0. So then I will have to choose my interval of interest. So let's say I want to study beta, I'm sorry, from 0.2 up until the value of 1. And of course, I have to choose an iteration step for this for loop, okay? The smaller the step, the more detailed the diagram will look. So let's go into the loop of the diagram. We start from beta equals 0.2. Okay, so what do? We simulate the system, and for this we need to simulate the system for a lot of time. I would say 1,000+ seconds. We discard the transient behavior. This is extremely important. Okay, the transient doesn't count. So the first 100 seconds, maybe more, maybe 200, maybe 300 seconds, depending on the system, you discard it. Okay, you don't take it into account. So after I'm left with the rest of the trajectory, let's say from 200 seconds up to 1,000 seconds, I find the intersections with the plane of interest. So here we have the Lorenz system. As I told you in the previous graphs, I'm using this plane of interest, x1 equals 0. I also choose a direction, the negative derivative for x1. And for this time series, I find all the intersections, with a given plane. Okay. After I have found the points of intersection, I pretty much simply go to my graph and plot these points. Of course, I plot beta. So on the x-axis, I plot the value of beta that I'm currently at. Okay. And then I plot one of the other states. Obviously, the plane is x1 equals 0. So I don't have to plot x1, obviously. It's always going to be 0 at the intersections. So I can either plot the value of x2 at the intersection or the value of x3 at the intersection. You go with one, doesn't matter which one you are going to choose. Okay. So after I plot all of these intersections, what do? I go to the next simulation. Okay. So I change the value of beta to 0.2 plus this iteration step. Okay. But before I go to the next simulation, I do one more change. I set my initial conditions to the final value of my time series. Okay. Now, this requires a lot of attention. In the literature, you may find this step to be optional. Also, you may find some differentiation in how the diagram is named, depending on whether you use this step or not. Some papers, when you do that, when you reinitialize the initial conditions as the final values of the previous simulation, when you do that, they call this diagram the continuation diagram. Some others call this diagram the bifurcation diagram. Okay, I think the more correct term here is the continuation diagram, right? But let's call it for the moment bifurcation diagram, and I will explain it in a later video. Okay, so after we have finished by plotting the intersection with the plane, we reinitialize the initial conditions by using the end values of the previous time series. Okay, and we repeat this process until we finish with all the parameters. So the result we're going to get looks like this. Okay, and this is amazing. Okay, it gives us a lot of information, but first looking at it, it may make no sense. Now, let me give you an understanding. Here, beta in the x-axis is the parameter under study, and on the y-axis, we have the points of intersection with the plane x1 equals 0. Okay, and for these intersections, we plot x3. So what does this tell us? Okay, it looks beautiful, of course, but let's look at it more carefully. It tells us, that for all these values of beta here, we only have one intersection from the given plane, from 0.2 to 0.50 something, okay? So you can understand that here that I have only one value in the bifurcation diagram. What it signifies is that for this parameter value, the trajectory is periodic with period 1, because I have only one intersection with a given plane. And this point right here, the x3, is what I plot here, okay? Then you will see that around 50, 55, as we saw, 51, 52, this line right here is cut in two. Okay, it bifurcates actually and becomes two lines. So what does it tell us? It tells us that for this set of parameters around this region right here, we have two intersections with the plane, much like we saw earlier. So here we have these 2 points of intersection with the plane of interest. And that's why we have 2 lines in the bifurcation diagram, right? Then if you look closely, you will see that we have 4 lines. And this tells us that for this parameter right here, somewhere around 57, I guess, beta equals 57, we have 4 intersections with the plane. So we have a period 2, right? On the other hand, on these dense regions that you see that they are very dense, I don't have a clear amount of intersections, a clear amount of dots. This means that we have chaos. So for example, for beta equals 1, which we showed earlier, this vertical amount of innumerable dots lets us know that we have numerous intersections with a given plane. Okay, so we have chaos. So all of these dense regions right here indicate chaotic behavior. Okay, and that's why this graph is so useful. It gives us an immediate information of what periodic values give chaos and what periodic values give periodicity. What parameter values, I'm sorry, give periodicity. So for example, if I choose beta from 0.2 up until 0.5, I have periodic behavior. Then, and of course, all of these values have period 1 behavior. Then the period increases. So for this small region right here, I have a period 2, then I go to period 4, etc. And then I go into chaos. For beta equals 0.65 or 7 around here, what do I have? I have periodic behavior. So I also understand that because here I have one intersection. Okay, then I go into this transition into chaos. Then for some small values, I have periodic behavior again, and then chaos again, and then some sort of very small region where I have periodicity, and then chaos again. So you can see that I immediately understand which parameter values give me chaos and which give me periodic behavior. But not only that, I also understand qualitatively how we transition from period to chaos, okay? Because I see that as I increase my parameter, I have a period 1, and then the period becomes 2 and 4 and so on until it transitions to chaos. So this phenomenon here is called period doubling route to chaos. And then I observe that as I increase my parameter, I abruptly exit from chaotic behavior. So I have chaos here and I abruptly go to periodicity. And then as I increase it a bit further, I again go through a period doubling route. It's very small, but it's clear here. You have a period doubling route to chaos. Then the attractor is small, but then the attractor becomes larger. That's why I have intersections in many different parts. And then I get into periodicity and chaotic behavior. So I immediately understand how I go back and forth into chaos and out of chaos, okay? So this phenomenon is called period doubling route to chaos. Here the attractor becomes from small, suddenly becomes larger. This is called crisis of the attractor or expansion of the attractor. Then from chaos, I go abruptly into periodicity. So again, this is a crisis phenomenon. So as you can understand, I can understand and, qualitatively judge how we go back and forth from chaos into order, right? And of course, the more detail, the smaller the iteration step, the more detail you're going to get. So obviously here, for example, I rerun the bifurcation diagram only on this region, but I chose a much, much, much smaller step. So you can see that this region right here looks this way. So here the period doubling route is much clearer, right? You go from period 1 to period 2 to period 4. And maybe if I zoom in even further right here, you can see that the period 4 becomes period 8. The period 8 actually becomes period 16, but you need to zoom in again and again and again and again. And of course, the phenomenon is amazing. You can see a sort of fractal-like structure because you can see that this period doubling repeats here, but we also get some gaps where we go in and out of chaos, which are very, very, very small. So you can see this sort of self-similarity as we move in and zoom in with a smaller and smaller and smaller step. And of course, this is one of the amazing phenomena that appear in chaos. So you can do the same thing with all of these regions right here. You can choose a very small iteration step and obtain highly detailed bifurcation diagrams for very small regions. So the bifurcation diagram, overall, it's a great graph, far too many information revealed. So down below the description of the video, I'm going to give you MATLAB codes for the bifurcation diagram. And I'm also going to have one more additional video where we go step by step into the code of the bifurcation diagram and explain it. But if you understand this video, you will have no problem understanding the code that's in the description. So thank you very much, and I'll see you in the next video.